So when I first learned about LTP, I sort of sat there and listened, and I said, "No, hang on, there's a problem here, right?" Coincidentally, LTP-like events must sometimes happen, right? That if cell A is being fired by some strong input, well, occasionally cell B must fire at the same time, and so its inputs will end up being connected until eventually cell B is a strong input too, and then anytime cell B and cell C help make the cell fire, well, then cell C is going to get potentiated, and eventually all synapses will get potentiated, right? That if it can happen coincidentally once, then that will make it more likely to happen coincidentally the next time until eventually, shouldn't you get a seizure, and what's stopping that? Now, it's probably more complicated than what I'm just about to say, but there is also LTD, long-term depression, where low frequency input, but for a long time, makes the um, makes the input weaker, right? So here's one of the original papers by Dudek, whose name I'm forgetting right this second, and Mark Beer, and Serena Dudek, and they're doing a nice two pathway stimuli. So they've got input one, input two. Input one gets this low frequency stimuli, and you see after they've finished doing the low frequency stimuli, input one is sort of down by about 30% from where it started, and after the best part of an hour, it's still down 20%, while input two, that didn't get the low frequency stimulus, is fine. Um, we actually see that there's sort of like a sliding scale, right? So again, this is from Serena Dudek. So if you change the frequency of the conditioning stimuli at about this 1 to 3 hertz range is key LTD. So once a second to 3 times a second, you get the most amount of LTD. Much lower than that, and you don't change the size of the EPSP at all. At about 10 hertz on average, then you just don't change the weighting. That's sort of the mean. And as you start going higher and higher in frequencies, then you start inducing LTP, right? So we've got this curve where, depending on how frequently the input comes, decides whether you get LTD or LTP. Now, LTP is NMDA receptor dependent. So is LTD, right? So here they are applying good old AP5, APV, same thing. They apply their 1 hertz stimuli, nothing happens to the EPSP size. Then they apply it without AP5 around, and we get our good 25% LTP. I want to add LTD. I said 25% LTP before, 25% LTD. I want to add that LTD can be induced in other mechanisms as well that are NMDA receptor independent. And to be honest, there are LTP mechanisms that are NMDA receptor independent as well. But things get really cool when you find out that you can basically flick a synapse up and down in size with either the low frequency stimuli or the high frequency stimuli. So that's what they see here. So on the black channel, they do a high frequency stimuli, up it goes, right? Then they do a low frequency stimuli, back down it goes. Here they're doing it and flip the order. So they do a low frequency stimuli first, drops down, then they do a theta burst stimuli, a high frequency stimuli, and up it goes again. So um, we we can see that this really does seem like a plausible memory mechanism, that it we can sort of ramp things up and down. It's specific to inputs. Uh, it's got all of the markings of a good mechanism for storing memory. Now, what about LTD, right? So I gave you this idea. LTP is caused by strong postsynaptic depolarization. Clears the magnesium blockade from NMDA receptors. This allows glutamate to allow calcium to come in. That calcium activates calmodulin, which leads to CAMK kinase. Calcium calmodulin dependent kinase being active. This phosphorylates AMPA receptors. We also see an increase in protein synthesis. All right, that's all fine, right? That's the pathway. But how does LTD happen, especially if LTD is also NMDA receptor dependent? How? So the classical hypothesis is sometimes called the calcium hypothesis. Basically says that brief, strong calcium elevations make LTD, while smaller, more prolonged elevations make LTD. Did I say that right? Big, short elevations LTP, smaller, prolonged LTD. And we're basing this on the idea that calcium chelators can block both LTP and LTD. Calcium uncaging can produce both LTP and LTP, LTP and LTD, depending on the level and the time course of the calcium. So if you make the calcium rise huge and fast, you get LTP. If you make it small but last for a longer time, you get LTD. And thirdly, electrophysiological protocols that produce LTP are associated with a high calcium influx, while ones that produce LTD are associated with a low calcium influx. And you can actually see in this paper showing how EGTA, a calcium chelator, well, when you apply it at a very low concentration, right, they get nothing, suggesting here that they are right at that sort of LTP, LTD threshold point where they're stimulating just enough to be right between getting LTP and LTD. But as they increase the concentration of EGTA and it slowly remove the amount of calcium, then they start to see LTD. But then as they remove all of the calcium with an even higher concentration of EGTA, you'll have to forgive them putting this axis in the wrong direction. It's very bizarre, but here they've got even higher concentrations of EGTA. The LTD fails again, right? So there's the sweet spot where where the calcium has to be not too big, not too little, to get LTD.